All right, physics reaction video number 35. This looks to be like a lecture or something, just because it's so long. It's 1946, yeah, and it's called Chapter 17, number 2, I think. So here we go.
So, well, it's 2:30, so I'm going to start recording just in case no one shows up today.
Aw, that stinks.
Sure. So what I'm going to do is I'm going to do the questions that we had to do for work today, which were at 17, chapter 17, section 2, talks about capacitors.
Ooh.
Capacitors is a device that stores electrical potential energy. It actually turning the frequency of the radio receiver is a capacitor. Eliminating spark in an automobile ignition system is a capacitor.
Cool.
Stores energy in electric flashes. Those are also capacitors. So if we look at what we were doing today, is we're actually looking at how the capacitors work depending on the size and the shape of the capacitor.
Quick story of capacitors. So I worked on a ruby laser when I was in graduate school, and ruby was actually the first thing that they sort of made a laser out of. It turns out it's a 3-level laser instead of a 4-level laser, so it's not as efficient. Basically, what happens in a laser is you have more electrons in the upper state than in the lower, which is impossible from a temperature perspective, but you pump it and then they all fall back down. But if you just have a 2-state laser, every single electron that goes down, the next photon that comes through, it can reabsorb it. So what you need is a way to clear out this bottom level. And so usually a 3-level starts down below, pumps them up, and then this is the laser, and then they rapidly get out of there. They get out of there so they don't absorb the laser. 4-level laser just has a 4th one up here, so you overpump them, and then this is not a very stable place, because if it was stable, they would just immediately re-emit and come all the way back down. So they come down over here, and then they just gather, and shoot. Okay, little ruby laser history. But they store the flash lamps, the energy for the flash lamps, in monster capacitors. We're talking huge. And unfortunately, the ruby laser that we had occasionally would not discharge. So it's not the ruby's fault. The ruby crystal was doing its job. But you would hit fire and nothing would happen. The flash lamps wouldn't go. You wouldn't get this blast of ruby laser light, and you'd have these charged capacitors. So we had this metal rod, I don't know, 4 feet long, something like that, and half of it was covered in plastic. And so you held onto the plastic and you stuck it in the capacitor, and you just touched both walls. And the first time I did it, my advisor was like, oh yeah, it's easy. You just have to discharge the capacitors. No problem. Just do it. And everyone else, I didn't notice until later, moved far away, because it's not dangerous to your hand, but it is so stinking loud. I couldn't believe how loud it was. Oh, so I hated that thing. So every time I teach capacitors, that's what I think about.
So, and then they gave us some units. So the main ones that you need to have is you need to know that F stands for Faraday, and that equals coulombs per unit of voltage. You also will need to know C equals Q divided by the change in V, which is the magnitude of the charge in a plate over potential difference.
So I love how she's modeling that, hey, all this stuff's in your book, folks. Just turn the page and find it. And the units, of course, super, super interesting. I think that all of these combined units, there's a reason for them, right? You could just break it all down to their basic SI units. So what are the basics? So you got joules, coulombs, time, newtons, I suppose, if you want to, meters and kilograms, although you don't tend to use kilograms a whole lot in these sorts of problems. But there's certain combinations that we use so often that we just name these things. We're sick and tired of saying them all. We name them. Now, oddly, the physics community has refused to do that for kilogram meters per second, also known as palms, which is what I call the unit of momentum. And yet for every single stinking other thing we do, we've got farads, and we've got all of these things that we do for for all these other calculations.
You also will need to know that C equals that epsilon, which is a funny looking E. O and A over D. So what we're going to do is I'm going to go ahead and go into the practice problems. But before I do want to talk a couple of things I thought was important. When you're talking about material between a capacitor.
So I'm just going to pause here. Here's what I love. And this is just she's modeling it so well. She says a couple of things that are important, right? So she of course knows this material super well. She of course, knows this book really well, but she's trying to help them realize, okay, it's intimidating. There's so much stuff in here, but I really think that there's some things that we have to hit home, and very likely I'm going to assess you on. So we might as well pay attention to that. Now, question for my viewers here is, how do you both do that and keep the students from only paying attention to that and skipping everything else, right? So I really struggle with that, because if I say this is important, or if I write it on the board, boom, that's it. That's all they care about. They're like, okay, that's the only thing he's ever going to test us on, so I can skip all the rest of this. And so I've really struggled with that, and I've tried lots and lots of ways to approach that, including basically jettisoning the textbook, lots of things. And so I feel like what she's doing here, she's modeling the fact that, look, we have this fantastic resource. Also notice that she's talking about a third party, like an author or something, giving all of them something. So she's putting herself in the same shoes as her students, which I think is a really cool way to go about doing it.
Capacitor plate that can change the capacity is a dielectric. And what that is that's the material between a parallel plate capacitor. Insulators known as air, rubber, glass, and wax paper would be in between there to help discharge a capacitor, to help with that. So let's look at question number 1 on page 595.
Let's do it. 595.
So 595, it says that is a 4 UF capacitors connected to a 12 volt. What is the charge of each plate of the capacitor? So the first thing that I would like you to do is I would like you to draw a circuit.
Of course.
So if we're drawing a circuit, the first thing that you would need to know is this right here actually states for a battery.
Cool.
And then what?
Someone was pointing out to me the other day that battery really means collection of things, right? And so typically, like the AA, AAA, all of that stuff is a stack of cells. Usually they're like 1.5 volts. And so, no, I'm saying that wrong. It must be less than that. Because typical batteries are 1.5 volts. And my point is that they're made up of tiny little cells, each one of which only gives a tiny little bit of voltage, but you stack them all up until you get the 1.5 volts. So they're pointing out that certain cells aren't really a collection of them. You can buy single cells. I think they were talking about watch batteries or something. And so why do we call those batteries? And it points out to me this crazy use of the English language, right? That honestly, students think the word battery means two things. It means this electrical thing that you use to power electronics, and it means this collection of things when you're talking about like soldiers or things like that. And so, but really it's the same word, and I found that really fascinating.
What we have is we have a capacitor. So we're going to do a circle, and we're going to do a C. That's going to tell us it's a capacitor.
Love it.
So what happens is you have a positive and a negative on your battery. This right now is basically telling you there's two batteries. Circuits are going around, and this capacitor changes the amount of voltage there. So it says, what is the change on each place of the capacitor? So the first thing that you want to do.
So it's interesting, right? So if she were in class right now, if literally students were there, they would have said charge when she said change. I mean, easy mistake, right? You're reading fast. Change and charge look quite similar. But it's interesting that particular mistake, it can cause some confusion to students, because we do use the word change a lot, change of voltage, change. And so she meant charge. And so it's one of the losses we have with this remote teaching when we don't have a live audience. Some of us are better than others at dealing with that, right? When students say, you meant charge. Like, I used to get defensive, stupidly. I used to get defensive, like, oh, no, actually, you know what I mean? Or I would really like shut down, oh, you're right, never mind. And I think that, come on, there's just no way we can always get this stuff right. And so I really like an active classroom where I really try to brainstorm ways to help students feel free to do that kind of thing. But it stinks, right? Because in this online thing, I'm sure when she watched this later, she's like, oh, of course I meant charge. And we've seen some people before who have like used post editing, and they'll say, well, I meant to charge. But come on, we don't have the time for that always. So let's keep going. This is great. Oh, quickly on the C for a capacitor, right? So sometimes we use the 2 lines for capacitors, and of course students are like, huh, what? Doesn't even look like it's a circuit anymore. And of course that's the beauty of capacitors. They're not really a circuit. They kind of break the circuit. But to say that it's just this thing with a C in it, I wonder if she does any other electrical components that way. Like you could do a resistor that way, you could a circle with an R. You could do an inductor that way, a circle with an L. So I am curious why she didn't put the capacitor over here. I mean, that just naturally to me seems like where it would go. Of course, it doesn't matter. So maybe from that perspective, like training the students to know that it doesn't matter, that's really interesting. But I'm curious to see how she follows up with this.
Is you will want to write down your variables.
Of
so
course.
my capacitor is 400 US. My change in voltage 1, well, it's a 12-volt battery. So that would be 12 volts. And then my voltage 2 is going to be 1.50. So you need to have all that first. So if you draw the diagram showing the capacitor, showing that you have a voltage of 12 voltage, and then as it goes through with the voltage 2, 1.5, which we're not really going to specify right now, but we could specify it later once we start drawing these type of circuits.
Cool.
So the first question is asking us about Q. So we're going to use Q equals C times the change in voltage 1.
So I used to tell my students QVC, like there used to be a TV show that would sell things, QVC. But the problem with those mnemonics, right, is where does the equal sign go? Right? Oh, QVC, that's an easy way to remember that. QVC, right? Well, the equal sign needs to go after the Q. So that's when I really started to drive home the physics, constantly driving home the physics. The capacitance is telling you it has a high capacity. If it has a high capacity, it can store a lot of charge without you having to hook it up to a very powerful battery, right? So if you look at how this works, if you put the delta V over here, so if the only way to make C big is either you make Q big or delta V small, and so it has a high capacity to store a lot of charge. So if C is big, Q is big. But frankly, if you're in a hurry, QVC, right? When I'm lecturing or something like that.
So if we look at C, we have these units of UF, and what we're going to do is we're going to change that to F instead. To be able to do that, we're going to move our decimal place over. So now our C equals 4.00 times 10 to the negative 6 Faraday. And we're going to multiply that by our voltage, which is 12 volts. So if you take your calculator.
So here again, a small inconsistency. Either there's supposed to be a decimal place here, or this is supposed to be minus 4, right? Because it's 400, not 4 microfarads. So let's see where that sort of shows up. So either she's going to go through, and then my guess is there was supposed to be a decimal place here, or maybe frankly there is one, and we just can't see it or not. And so we're going to get an answer here pretty soon. So let's see, if she leaves this alone, she's going to get about 4.8 times 10 to the minus 5 coulombs. And if she does it this way, she'll get 10 to the minus 3. So let's see.
Make sure that your mode is right, which mine is right this time. So what I'm going to do is I'm going to take 4.00 times 10 to the negative 6, and I'm going to multiply that by 12 volts.
So it was interesting to watch her do that calculation. I've been super frustrated with phone calculators because the times 10 to the button, on some calculators that's an EE, on some of them it's literally labeled times 10 to the, right? For some reason, the very first few calculators that were built for cell phones did not have that button. And you literally need to do what she did, times 10 to the negative 6th. And the only reason I hate that is when those types of things are in the denominator, because then that times brings it back up into the numerator. She doesn't have that problem here, so it's going to be fine. But I'm really curious what you guys have been doing with teaching your students the EE button or the times 10 to the button, right? Do you really encourage it? Do you say, well, let's just make it look like exactly like it looks on the screen? So hit times, then do 10 to the -6. Interestingly, as long as you constantly do the parentheses, then you're fine. You can stick it in the denominator all you want. But I'm always fascinated by that.
And I get 4.8 times 10 to the 5th. So your first answer is 4.8 times 10 to the -5th. But we're not done yet, because there's there is a second part of this problem. It says that the same capacitor is connected to a 1.5 volt battery. How much electricity is potentially energy stored?
Miss Mom.
What I'm going to do here is...
Whoa, that was cool. I might have to stop here. I don't think I should be showing students. Yeah, I better stop. So let me, sorry about that. So it looked like she does have a live audience. So I'm dying to sort of watch the rest, but frankly, I feel a little bit nervous showing student voices here, so I'm just going to stop. A couple of really interesting things, again, and I make these mistakes all the time, right? So she said 4.8 times 10 to the 5th, and then when she wrote it down, she said 4.8 times 10 to the -5th, and -5th is correct. And so there's these sort of things that a live audience can help so much with, and I'm really racking my brain to encourage students to jump in and say, oh, you meant negative, right? And some of them do it in a mean-spirited way, well, not mean-spirited, but almost like a show-upmanship way, and others are literally confused. I mean, for all we know, this particular student is like, you said to the 5th, but then you wrote -5th, I'm totally confused. And if we can receive that feedback, then of course we can fix it, including, frankly, that other decimal place thing. So these are really, really interesting problems. I loved what she did was sort of relay the usefulness of the textbook to really sort of help them think about how to read it. And I liked how she approached this problem really, again, as sort of a scaffolded thing, like, look, here's what we got, here's what's asking, let's plug away. And of course, what's a real struggle with these problems is that none of it makes any sense. 4.8 times 10 to the -5 coulombs, I don't know, what the heck does that mean? Right, the only thing that I know for sure is the charge on the electron, which is 10 to the -19 coulombs. So that's a gajillion electrons, but it just doesn't. There's just so little internal understanding of these numbers. I think that's what makes electronics hard. I think the only thing that we have experience with is voltage. We know that your car battery is 12 volts. Some people know that a AA battery is 1.5 volts. There's this thing called a 9-volt battery. So there's a little bit of that, but man, the rest of it, the resistance values seem to come out of nowhere, the capacitance values seem to come out of nowhere, and I think that's really, really difficult. Well, anyways, everybody, sorry to pause a little bit early, but I didn't really want to show student voices just because I don't have permission. All right, you guys, well, I hope you have a great day, and remember, physics teachers are awesome.